My name is Jacob Pushy, and today I'm going to walk you, the audience, through how oxygen binds to heme, and if any structural changes occur, along with explaining the binding capacity of oxygen to heme in the lungs, and how that differs from the capillaries. Lastly, I will explain how CO2 interacting with water can affect the pH of the capillaries. Hemoglobin is an oxygen carrier protein. Please excuse my poorly drawn hemoglobin here. That is found in red blood cells and is responsible for red blood cells' color. One single hemoglobin molecule consists of a globin group surrounded by 4 heme groups. Each heme group is composed of 1 iron atom, making a total of 4 iron atoms in 1 hemoglobin molecule. One hemoglobin molecule can bind up to 4 oxygen atoms. The oxygen transport occurs in a combined form with hemoglobin, and a very small amount is transported in dissolved form. The binding of oxygen onto the hemoglobin occurs in a cooperative manner, meaning that the binding of one first molecule of oxygen facilitates the easy binding of the second oxygen molecule, and so on. There are 2 states of hemoglobin, the T and the R, T being tense and R being relaxed states. When the hemoglobin is not bound to oxygen, it is said to be in the T state, meaning tense, having a low affinity for oxygen. As the first oxygen molecule binds to the hemoglobin molecule, it alters the shape of the hemoglobin to the R state, having a higher affinity than the T state. The binding of the oxygen to the hemoglobin is defined as the function of the partial pressure, resulting in a sigmoidal-shaped graph. At the lungs, the PO2 is higher, and the hemoglobin becomes saturated with oxygen. For a more anatomical perspective, I'll say that I would like to discuss the oxygen being transported to the blood from the lungs, because the partial pressure of oxygen is relatively higher than the tissues, where the partial pressure of oxygen is much lower. In the lungs, hemoglobin is saturated with oxygen, as I previously stated, on approximately 98% usually of the oxygen binding sites are occupied on healthy patients. Usually in the ICU, it's not the case. On the other hand, in the tissues, the saturated level drops to 32%, quite a steep drop. The binding of the oxygen molecule occurs at the 6th coordination site of the iron ion and substantially rearranges the electrons within the iron so that the ion becomes effectively smaller, which then allows it to move into the plane of the porphyrin. This change is taking place in electronic structure and magnetic properties of hemoglobin, which are the basis of functional magnetic resonance imaging, actually, MRI. On oxygen binding, there are substantial changes in quaternary structure that correspond to the T and the R state transition. In the lungs, oxygen binds to heme, and in the capillaries, oxygen dissociates from heme and mixes in the blood. So, the binding of oxygen is facilitated by the low carbon dioxide concentration, high pH, and low temperature. Okay. And here's a little great image I found actually to kind of illustrate that. It's the oxyhemoglobin dissociative curve there, and then you kind of have the affinity for oxygen and the hemoglobin there. So, at the tissue level, oh jeez, it's so hot today. Everything's sticking to me. At the tissue level, the cells utilize the oxygen to carry out the metabolic processes, producing carbon dioxide in the process. The carbon dioxide is transported into the blood at the capillary end, which then reacts with the water to form bicarbonate and hydrogen ions. The production of hydrogen ions results in the reduction in the pH at the capillaries or tissue level. Low pH and accumulation of carbon dioxide facilitate the reduction in the affinity of the hemoglobin for the oxygen molecule, shifting the curve towards the right and releasing oxygen at the tissue level. This occurs because at greater H plus ion concentration, various amino acid residues such as histidine stabilize deoxyhemoglobin in the T state. The T state has, as we've stated, a lower affinity for oxygen than the R state. So, with increased acidity, the hemoglobin binds to less O2 for a given PO2. This is known as the Bohr effect. As CO2 is acidic in nature, so when it interacts with water, then the pH of the capillaries decreases. And so, that is my explanation of how, firstly, oxygen binds to heme, and if any structural changes occur, along with explaining the binding capacity of oxygen to heme in the lungs, how that differs from the capillaries, and how CO2 interacting with water can affect the pH of the capillaries. So, thanks again, guys, and please leave your comments and questions below.